Welcome back. Today we begin our new unit on energy by attempting to define what energy is and what it can do. A definition of energy is hard to agree upon because it can take so many different forms. Sometimes, in fact, I wonder if energy itself even exists, or if it's just a mathematical construction that's so useful because it can be used in so many different places and so often simplifies calculations. Regardless of whether energy actually exists or not, let's attempt a loose working definition. One might be an object's ability to do something, and I'll put that something in quotes. It could take a lot of different forms. This something could be to move something, or to accelerate or decelerate something, to rotate something, to stretch or shrink, to warm something up or cool something off, to produce sound or light. In short, this something usually has a name. We call it work, and we'll define that specifically in just a moment. Now, as mentioned earlier, energy comes in many different forms, and we'll study several of these in detail. First, it can come in several different types of potential energy, usually gravitational potential energy, or electric, or chemical. It can also come in the form of motion, in which case we call it kinetic energy. Or it can come in the form of heat, which is sometimes called thermal energy. And there are even ways of using energy in light and sound calculations. Now, energy has specific units. The standard unit is a joule, and that uses a capital J because it's named after the person, James Prescott Joule, who helped make a lot of the original calculations about energy. In the English system, there's also a unit, and that is the foot-pound. Now, energy, because it comes in so many different forms, has a lot of different units. The centimeter-gram system has a unit called the erg, which we probably won't see too often, but it is extremely tiny. 10 million ergs makes up 1 joule. Probably in America, the most common unit is a kilowatt hour. This is what's measured on your electricity bills. And to give you some idea of that, that's about how much energy would be required to run 10 light bulbs for 1 hour. If you're talking about thermodynamics, we tend to use the British thermal unit, or a BTU, quite often, or the metric version of that, which is a calorie. Why don't you take a moment and write down some of these conversion factors for energy. Now, energy is the ability of an object to do something, and that something is often described as work. So our first specific type of energy that we'll study is that of work. A definition of this is when you transfer energy from one object to another, or from one form to another, by applying a force on an object for a specified distance. There are a couple formulas for this. Specifically, work could be just calculated as the amount of energy that got transferred. More often than not, we use the formula that work is a force exerted on an object times the distance that it was exerted on. With one stipulation: when that occurs, the force that we use must be the component of the force that's exerted in the same direction as the distance. If you apply a force at an angle, you'll have to break that angle up into components and use the component of the force that's parallel to the movement. For you math dorks out there, work is technically a dot product of the vectors of force and distance. So let's look at some examples. Suppose a 105-gram hockey puck is sliding across the ice, and a player decides to exert a force on it using a stick. So he exerts a force of 4.5 newtons over a distance of 15 centimeters. How much work did he do on the puck? And therefore, what is the change in the puck's energy? This is a simple enough calculation. The formula for work is force times distance. And these two numbers were both given to us in the problem. The force that the player exerted on the puck was 4.5 newtons. And the distance over which he exerted that force was 0.15 meters. And multiplication of these two numbers gives us 0.675. And the units for that would be Newton meters, but nobody ever calls energy units Newton meters. A Newton meter is the standard unit of force, standard unit of distance. That corresponds to the standard unit of energy, which is a joule. So 0.675 joules. What that means is that whatever energy the puck had in it originally, now it has 0.675 joules more. So if its original energy was 10 joules, well, now it has 10.675 joules. Or if we know how many joules of energy it has now, suppose it has 20 joules now, we could figure out what it had originally by subtracting 0.675 joules. So originally it might have had 19.325. For a slightly more complicated example, suppose you're taking your dog for a walk and all of a sudden they decide to stop and not want to move anywhere, and you need to drag them back home. Suppose as you're dragging, you have to pull with 150 pounds of force on their leash for about a quarter mile with the leash at an average angle of 25 degrees. How much work was done, or as a more practical example, how many more calories did you burn than you would have otherwise? To answer this question, the first thing I need to know is that the force that we exerted on the chain was 150 pounds, but that was not in the exact direction that we pulled. What we need to do is to calculate how much of that 150 pounds was in the direction of our motion. So if we draw a triangle, 150 pounds, and that was at an angle of 25 degrees, we need to figure out what component of that 150 was parallel to the motion, because that's what gets used in our work calculation, and what component of that 150 was perpendicular to our motion, and that for now we will neglect. To answer this, we'll simply do 150 cosine of 25 or 150 sine of 25, and based on our drawing, it'll be the bigger of the two numbers. So 150 times the sine of 25 gives us 63 pounds, and 150 times the cosine of 25 gives us 136 pounds, and since that's the bigger of the two numbers, and that, according to the drawing, should be the bigger side, that's the number we'll use. And in general, we typically use the cosine for these because most often the angle that is given to us is the angle measured from horizontal. But you always need to check and make sure that that's the case. So our work calculation then is still force times distance. But this time, instead of using the 150 pounds, we'll use 136 pounds. And our distance is given to us as a quarter of a mile. We should convert that into the standard English unit of feet. So 1/4 of a mile times 5,280 feet. And this gives us an amount of work of 179,520 foot-pounds. Now, I hardly have any idea what a joule is. I have no clue what a foot-pound is. To give you some idea of this, this would be the energy it would take to lift 1 pound up 179,520 feet, or the energy required to lift 179,520 pounds up 1 foot, or some other sort of combination that multiplies out to that. Or we can convert this into calories, something we're a little more familiar with. To do that, we'll start with 179,520 foot-pounds. And we'll have to do a couple conversions to get that into calories. The first conversion I'll do is to convert from foot-pounds into joules, and that conversion is 746 joules is equivalent to 550 foot-pounds. If you wonder why I use that weird fraction of numbers, you'll have to watch the power video because those are both related to a horsepower. And then to convert from joules into calories, there are 4.148 joules in 1 calorie. And if we stop now, we'd get an answer of 58,700 calories, and you'd think, oh wow, what a workout. But unfortunately, these calories are not the same type of calories that we typically talk about. This is a single calorie, and nutritional calories are actually kilocalories, or thousands of calories. So if you eat a 2,000 calorie diet, you're really eating a 2 million calorie diet. But anyways, that conversion is simple enough. 1 kilocalorie, often with a capital C, is equal to 1,000 calories. And this multiplication works out to be about 58.7 additional calories, as we consider them usually when we're talking about food. So that's in addition to the normal calories that you would have gotten just from walking anyways. So there's a brief introduction to energy and a specific type of energy called work. Tune back in next time as we start talking about a couple other types of energy, including potential energy and kinetic energy. Thanks for listening.